Hi, this is Alex from devstories.eu, Mastering DeepChem, episode 13 of 15. You have a newly mapped 3D structure of a viral protein, but finding where a therapeutic drug can actually latch onto it is like trying to place a single puzzle piece onto a 10,000-piece jigsaw floating in 3 dimensions. You cannot just throw a small molecule at a massive protein and hope it sticks. You need to map out the structural grooves first, and that is exactly what binding pocket discovery is for. Before going further, let us clear up a common misunderstanding. Pocket discovery does not place a drug inside a protein. It only surveys the empty real estate to find potential binding sites. Generating the actual position of the molecule inside that site is called pose generation. That is a completely separate step. Today, we only care about finding the empty parking spots. In DeepChem, this workflow begins with the binding PocketFinder base class. This is an abstract template. Its job is to provide a standard interface, taking a 3D macromolecule as input and returning a list of potential pockets as output. By using a base class, DeepChem ensures that whether you use a built-in algorithm or write your own, the pipeline remains consistent. But the actual heavy lifting is done by specific implementations, the most common being the ConvexHullPocketFinder. The ConvexHullPocketFinder algorithm algorithmically analyzes the 3-dimensional geometry of your viral protein. Picture wrapping the entire macromolecule tightly in shrink wrap. The wrap stretches straight across the gaps, clefts, and crevices on the surface. That outer boundary is the mathematical convex hull. The empty spaces trapped between that flat outer boundary and the actual bumpy atomic surface of the protein are your potential binding pockets. These are the vulnerable grooves where a new drug might successfully anchor. To identify these spaces systematically, the algorithm divides the volume around the protein into a fine 3D grid. It sweeps through this grid and identifies voxels, which are tiny 3D boxes. It looks for voxels that sit inside the convex hull but do not contain any protein atoms. It also measures the distance from these empty boxes to the nearest protein atom. If a box is too exposed to the surface, it is ignored. If it's buried too deeply inside the protein core, it is also ignored. The algorithm clusters the remaining valid boxes together to form the continuous shapes of the surface cavities. Once it maps a cavity, the finder generates a bounding box around it. Here is the key insight. The algorithm does not cut this bounding box perfectly to the exact dimensions of the hole. It adds a calculated layer of padding around the edges. This extra margin is critical because molecules in biology are dynamic. When you eventually hand these pocket coordinates over to a docking algorithm later in your pipeline, that padding provides the necessary wiggle room. It gives the next step enough surrounding space to calculate how the drug might twist, rotate, or shift as it settles into the groove. You pass your viral protein into the ConvexHullPocketFinder, and it hands you back a clean array of padded bounding boxes. You now know exactly where the structural vulnerabilities are, and you can focus your computational resources purely on those specific coordinates. If you want to help keep these episodes coming, you can support the show by searching for DevStoriesEU on Patreon. The padding ensures your downstream docking simulations will not fail simply because they bumped into an artificial mathematical wall. That's all for this one. Thanks for listening, and keep building.